Hi, in this video, I'll show you how to determine the convergence or divergence of an infinite series that contains a sine or a cosine function. I'll be showing how to do these two examples. They look very similar, but they have different outcomes, and that's why they make good examples for this. The reason why a lot of exercise and homework and exam questions in a calculus class put sine and cosine into an infinite series is because sine and cosine are periodic functions. They go from 1 to 0 to -1 to 0 in a cyclical manner. And therefore, in order to do those problems, you want to know what those sine and cosine values are. And usually they're very nice. They're either 1, -1, 0, or some very known function. And because it's cyclical, they repeat. And from that repetition, you should figure out the pattern of those numbers. These are the two examples. They both have sine in it. There's a pi inside of that and some factor. And the factors are different by a tiny little bit. Over here, this number is n, and over here, this number is 2n. Let's do the first one first. The way you approach these series with sine and cosine in it is to try out a few values of that sine and cosine so that you can see the pattern of the numbers. So let's try out some of these. 0, 1, 2, 3, 4. When n is equal to 0, we're looking at sine of pi over 2. And sine of pi over 2 is 1. When you have to deal with sine and cosine, always draw the unit circle on the side so you can visually see where things are. So first we're at pi over 2, and I have sine equals 1. When n is equal to 1, then I have 3 pi over 2, and sine of 3 pi over 2 is down here at -1. When n is equal to 2, you get 2 plus 1/2, 2.5 pi, that's 5 pi over 2. 5 pi over 2 is what? 1 pi over 2, 2 pi over 2, 3 pi over 2, 4, 5 pi over 2. I'm back here at 1. I'm already seeing the pattern. Next one is n equals 3, 3.5, that's 7 pi over 2. I was at 5 pi over 2 here, 6, 7. Then I'm down here again at -1. I see the pattern already. I'll just do one more just in case. 4. 4 plus 1/2 is 4.5. 4.5 is 9 over 2, so 9 pi over 2. And I was at 7 here. 8, 9. I'm back up here at +1. I see that the value of sine alternate between 1 and -1. And if you've done enough alternating sequence and alternating series, you know that this is a power of -1. Power of -1 to the power something. And you have to worry about whether or not is -1 to the n or -1 to the n plus 1, right? Odd versus even. Odd power is a -1. Even power is a +1. Well, in this case, it is equal to 1 when n equals 0. So it's this one, not that one. So I know that my sine is equal to -1 to the power n. That way I can substitute into the series. Another way to do the same thing is to work out the expression inside the sine. So I have sine n plus 1/2 times pi. I multiply this out, I get sine of n pi plus 1/2 pi. And I rewrite in the form that's familiar to me from trig class. And we tend to write it like this: sine of pi over 2 plus n pi. Now it's clear to me that that means I'm starting at pi over 2 here, and then I jump by pi. I jump by steps of pi. Or steps of pi mean I go 180 degrees, so I go opposite to the bottom point, and then I go opposite up to the top point and opposite to the bottom point. So yeah, I was checking a few numbers and I see the pattern. I do the algebra on the sine function, and yes, now I see that it does oscillate between the positive one on top and the negative one at bottom because it jumps by steps of pi. It jumps by 180 degrees. It's jump opposite of whatever the previous point is. Either way, I see that this is true. Since it is true, I'm going to substitute it into the series. I substitute this in, I got this series, and I recognize it is an alternating series. Well, an alternating series has its own convergence test called the alternating series test. And it goes like this. Suppose that we're given a series of -1 to power n b sub n, where b sub n is greater than or equal to 0. So that means we're taking the unsigned part of the series, the part other than the -1 to the nth. If we take the unsigned part of the series and we check that part, and if we have two conditions, if b sub n decreases, and it doesn't have to be decreasing the whole time, it just has to be decreasing after a certain point, right? At the beginning of series, we don't care. For little n greater than some capital N. So at some point, it starts decreasing. At the beginning, it could go up and down. And the limit of that b term is 0, then the alternating series converges. That is all it takes. A non-alternating series, this is not enough, because we've seen, for example, the harmonic series has decreasing terms and limit of the terms equal to 0, but it diverges. The reason why the alternating series converges with just these two conditions is because the minus and the plus cancel each other. The fact that they cancel each other helps a lot. So what happens in this case? The unsigned portion of the terms consists of 1 over 1 plus square root of n. This one decreases all the time because as n increases, square root n increases, 1 plus square root n increases, all of these things increase, but all of these things are in the denominator. And when the denominator increases, the whole fraction decreases. So we have bn decreases. The first condition is met. Now let's do the second condition. Limit as n goes to infinity of b sub n is the limit of this fraction. And this does go to 0 because the denominator goes to positive infinity. So limit is 0. Both conditions are met. Then we have this series, which is the same as the original one with the sine. It converges. And that's our conclusion for the first series. The first series is convergent. Now let's do the second series. Again, there are two ways of figuring out what that big sine expression is. One is to try a few values, and the other is to work out the algebra inside of it and see if we can get something out of it. Testing 0, 1, 2, 3 for now. If I need more, I'll add more. When n equals 0, we're looking at pi over 2, and sine of pi over 2, again, I'm going to draw a unit circle on the side, cosine here and sine here. Sine of pi over 2 is right here, is 1. N equals 1, we're looking at 2.5 pi. 2.5 pi is 5 pi over 2. 1, 2, 3, 4, 5. 5 pi over 2, I'm back at the starting point. So again, it's 1. N equals 2. We're looking at 4.5 pi, that's 9 pi over 2. 9 pi over 2. So this was 5, 6, 7, 8, 9. 9 pi over 2. Again, the sign is 1. N equals 3. 3 times 2 is 6. 6.5. 6.5 is 13 over 2. So 13 pi over 2. That was 9 here. 10, 11, 12, and 13. I'm back here again. They're all equal to 1. So I'm starting to suspect that the numerator is equal to 1 all the time. What happens if I actually work out the algebra inside the sine? Then I have sine of, multiply everything out. I have 2n pi plus 1/2 pi. And I rewrite in more familiar form, and that is sine of pi over 2 plus 2n pi. If I remember any trig at all, I will remember that the sine wave repeats every 2 pi. The period of sine is 2 pi. So that means all of this is just equal to sine of pi over 2, and sine of pi over 2 is just equal to 1. The numerator of this series is just equal to 1, so I can substitute it in, and the series becomes sum of n from 0 to infinity of 1 over 1 plus square root of n. So the convergence or divergence of the original series is the convergence or divergence of this series. And those of you who are quick with it can see right away that this series diverges. But let's go slow. What is this series most similar to? This series is most similar to what's called the p-series. A p-series is a series of this form where p is positive, but if p is between 0 and 1 inclusive, then the series diverges. If p is greater than 1, then it converges. When p is equal to 1, you have this series. It's called the harmonic series, and it diverges. If you don't remember all the rules about the p-series, at least remember that the harmonic series diverges, because the harmonic series is very useful in proving that other series diverge. It sits right at the margin of being divergent. Thus, for purposes of the comparison test or the limit comparison test, the harmonic series is very useful in proving that a series diverges, and that's why you should at least remember that part. If you're going to remember all of the p-series, even better. All right, so I look at my series, and I see it's very much similar to the p-series with p equals 1/2, this series. So I totally suspect that my series diverges, just like this series diverges, because it's part of the p between 0 and 1. Whenever I know of a series that's similar to my series that diverges or converges, I want to do either a comparison test or a limit comparison test. So let's see if I can do a comparison test. My series has 1 over 1 plus square root of n, and the series I want to look at has 1 over square root of n. Well, I know that this quantity is larger than this quantity. And so the reciprocal of it is less than. Well, being less than a divergent series doesn't help. When a series diverges, you want yours to be even larger. So you can tell that if this one goes to infinity, then definitely that one also goes to infinity. Whereas if you know that this series, this P series goes to infinity, and your series is less than it doesn't help. It could be infinity, or it could be finite. I don't know. I just know that it's less than infinity, and it could be whatever. So comparison test doesn't work. Then the next thing I try is a limit comparison test. The limit comparison test says divide the terms of the two series and take the limit of that. If that limit arrives at a finite number, then the two series converge or diverge together. So we take the ratio of one divided by the other. I'm going to take this one, I divide by that one. Some of you may ask, does it matter which one is on top and which one is in the bottom? And the answer is no, it doesn't matter. Because if this limit goes to a finite number, then if you flip it over, then it'll go to a different finite number. So either way, it will work. But the tricky part for me is I want my limit to look simple. So I think ahead of time that I want my ratio to be eventually this, because this is easier to simplify than if it were the other way around. And since I want this to be my ratio, I think backward and I want to put that squared 1 over squared n on top. But even if you got it the wrong way around, you're still okay. I'll show you that in a second. Right now, I'm taking the P series on top and my series in the bottom. And using the rules of dividing fractions, I end up with this, just like I want. And this simplifies to that because I break it up into two fractions. And this is just 1. So this is the limit as n goes to infinity of this, which is equal to 0 plus 1 equals 1, which is a finite number. That means both series converge or diverge together. And since the P series with square root of n, which is the series we started with, there we go. That's your answer. Now, I did promise that I'm going to show you how to do the limit if you divide it the different way. Let's say you divide the terms of the two series the opposite way of how I did it. You can still take this limit. It just takes slightly more steps. Dividing fractions, then I have squared n like this over 1 plus squared n. Well, I can't quite divide, so I'm going to take one more step. I'm going to add 1 and subtract 1 from the numerator. And now I can separate them just like before. This cancels to 1. And this limit is also equals to 1, also finite, and therefore both series diverge together. Same answer. Let me scroll up to the first example we did. And that was, in the first example, we figured out that this alternating series converges. But for alternating series, we have the concept of conditional versus absolute convergent, right? Conditional convergence means that we keep the alternating values as is, then yes, it will converge to some value. But is this absolutely convergent? Well, it's not, because for absolute convergent, you take away the alternating part, you have just the non-alternating part, and we've seen that that makes the first series for absolute convergence purpose, it looks exactly like the second series, and the second series divergent. So this first series is an alternate series that converges conditionally, not absolutely. So here's our answer. The first series is an alternating series, and it converges conditionally. And the second series diverges. Matter of fact, the second series is the absolute value of the first series. All right, hope that helps. Any questions or comments, put it in the comment section below. Like, share, and subscribe for more contents, and thanks for watching. Bye.